Thank you very much, Peter, for the kind introduction. And actually, I put a number of keywords in the title of my talk: proton release, oxygen evolution, water incorporation, everything. But today, I would like to focus on proton release, because proton cannot be identified even in the X-ray crystal structures, but proton can be identified using theoretical approaches, which I can contribute. And I would like to start with a brief introduction of hydrogen bond. Of course, everybody here knows what is hydrogen bond. Nevertheless, to form hydrogen bond, you need the donor and acceptor moieties. And generally, proton is located at the donor moiety, which means pK value of donor is higher than that of acceptor. And in that case, you will see the asymmetric shape of the potential energy profile and potential energy curve. And actually, the pK energy difference between the donor and acceptor moiety corresponds to the pK difference. Then what can you see if the pK values of the donor and acceptor moieties are equal? In such case, you will see formation of symmetric hydrogen bonds, including low barrier or single layer hydrogen bonds. In these hydrogen bonds, actually, distance is very short, sometimes less than 2.5 angstrom, and there is almost no barrier in between. So proton can easily move in between. And actually, low barrier hydrogen bond can be identified using DFT calculation. Of course, they can identify it in NMR studies, and here are the molecules which have been proposed to have low barrier hydrogen bond experimentally. And just using DFT calculation, you can see a symmetric shape of the potential energy profile of hydrogen bonds. So you don't have to consider, you don't have to solve even the nuclear Schrödinger equation to demonstrate whether they have low barrier hydrogen bonds, because it's just a matter of pKa values. And you can also see the presence of low barrier hydrogen bond in proteins. This is a case of PS2, the tyrosine and histidine pair, redox active tyrosine Z. And in Chen's crystal structure, the distance between tyrosine and histidine is extremely short, 2.46 angstrom. And if you perform typical DFT calculation for typical imidazole tyrosine molecules, you will probably get the distance of 2.8 angstrom. So it is extremely short. So originally, I thought something was wrong in his structure. So I performed quantum chemical calculations in the presence of protein environment, which we call QMMM calculations. Then unexpectedly, we reproduced very short distance even in the quantum chemical calculation. So anyway, this is quantum chemically justified. But I didn't understand why we have so short distance. So we analyzed the potential energy profile in the protein environment. And this is actually what we got for the hydrogen bond between tyrosine Z and histidine. This resembles that of the typical single-layer hydrogen bond, which means proton can easily move between tyrosine and histidine within this hydrogen bond. Why do we get the low barrier hydrogen bond? This is because of the presence of a cluster of water molecules near the tyrosine. And they are not bulk water molecules, but the fixed dipole. And actually, the water molecule, which I named W7, donates strong hydrogen bond to tyrosine, decreasing the pK value of tyrosine to that of histidine. So this is why we got low barrier hydrogen bond. Indeed, if we remove this cluster and perform QMMM calculation again, we don't see the formation of low barrier hydrogen bond anymore. The distance is lengthened to 2.71 angstrom, just a standard hydrogen bond. So, And of course, proton cannot move easily to histidine moiety because now we have an uphill energy barrier. So the barrierless hydrogen bond facilitates proton-coupled electron transfer in this case. And this is actually not only the case in PS2, even for QB. Yeah, QB is the terminal electron acceptor, and just before it becomes QB82 state, when I performed the QMMM calculation, I observed very short distance between histidine nitrogen and carbonyl oxygen of QB. It is 2.47 angstrom. And the potential shape is exactly the same as low barrier hydrogen bond. So proton can easily move from histidine to QB. So this is the protonation step, second protonation step of QB. So from my experience, I would like to say, I would emphasize, we always observe formation of low barrier hydrogen bond, even in the proton environment. Then why not about proton release of the manganese calcium cluster? It should not be exceptional. And we should discuss in terms of hydrogen bond energetics when we talk about proton transfer from the manganese calcium cluster. In Shen's crystal structure, there are a number of interesting points. And of course, I agree, O5 near calcium is an interesting spot. Yeah, I was originally started with O5 protonation stuff. But anyway, if you look at the hydrogen bond pattern of the manganese calcium cluster, you should not ignore the fact that the shortest hydrogen bond is it is the one which forms between O4 and W539, which is hydrogen bonding water to O4. So I started to analyze the potential energy profile of the hydrogen bond between O4 and W539. My policy is I don't manipulate the atomic coordinate in my calculation with respect to the original crystal structure. I also include PS2 proton environment, including the entire hydrogen bond network and proton acceptor groups. So, and this is the manganese calcium cluster, and in the neighborhood, there exists a chain of water molecules. They form the hydrogen bond network, and actually the hydrogen bond between O4 and OW539 forms the manganese calcium cluster is linked with the O4 water chain by this hydrogen bond between O4 and W539. In the X-ray crystal structure, the distance is less than 2.5 angstrom. And I think everybody agrees that proton should be in between. Otherwise, one cannot get such short distance. So I performed the QMMM calculation first in S0. Then I got the distance 2.55 angstrom. This is very short, but slightly longer than the one in the identified in the original crystal structure. And the potential energy profile indicates the proton is more populated at the O4 moiety rather than the water W539. However, when we oxidize the manganese calcium cluster to S1, then in my case, manganese 3 was oxidized. So the pK value of O4 decreased. Yeah, so pK value of O4 was decreased. So this is why we got formation. We got low barrier hydrogen bond between O4 and W539 in S1, and the distance is in agreement with experimentally observed distance in this case. So proton can easily move. And so now we have a situation where the proton in between can move easily, locally, but this movement propagates along the hydrogen bond network along the in the O4 water chain, and simultaneously, just in a single concerted step, proton arrives at the end of the O4 water chain. So this is how the proton, this O4 water chain works as a proton transfer pathway in the S0 to S1 transition. Here is the proton hydrogen bond pattern before proton transfer and after proton transfer. If we superimpose the two hydrogen bonding pattern, then you can see the presence of a number of H3O plus like molecule in the O4 water chain. This indicates oxygen atom did not move during the proton transfer along the O4 water chain. So the activation energy should be low for the proton transfer. And actually, this is consistent with experimentally observed fact that specifically low activation energy in the S0 to S1 transition, which has been summarized in Holger Dow's review. I skipped the second one. And also, the presence of O4 water chain could also explain the fact that S0 to S1 transition is less inhibited by chloride depletion because you don't see the existence of chloride along the O4 water chain. And here is the overview of the location of O4 water chain. Actually, it runs along the same axis as the electron transfer chain from the manganese calcium cluster to PD1 chlorophyll. So this means both electron and proton transfer pathways use the same electrostatic environment of PS2. And this makes sense. I also extended my study to further oxidized states. So I oxidized S1 to S2. In my case, I observed oxidation of manganese 4, the dangling manganese, which actually decreases the pK value of the ligand water W1. Yeah, because this is ligated to manganese 4. And also it has a proton acceptor aspartate 61. Due to the decrease of pKa of W1, now in S2 it forms low barrier hydrogen bond. Yeah, so now we have low barrier hydrogen bond between W1 and D1 aspartate 61. But proton doesn't go away from this side yet. And in S3, in S3, actually maybe people do not agree, but I observed oxidation W1 to OW1 dot minus instead of oxidation of manganese 1. But I am not the first one to suggest this result because Johannes Messenger and Chandra have already proposed in JAX 2001. The title of his paper is Absence of Manganese-Centered Oxidation in the S2 to S3 transition. And this is actually what we observed. Also, in this situation, we have negative charge on W1. So it attracts water molecule. And this, when we performed molecular dynamics simulation, a new water is coming and bind at OW1 dot minus, this guy, so which we call WNW1. And this water molecule is absent in the original crystal structure. People may think that the observation of O dot minus state or OW1 dot minus state in S3 is an artifact, but I don't think so. If you know simple chemistry, you can immediately understand because now here we have D1 aspartate 61, which the presence of D1 aspartate 61 facilitates proton-coupled electron transfer from W1, which decreases the redox potential of W1 for oxidation. And this is why W1 can be more easily oxidized than manganese 1 in the S2 to S3 transition. And I didn't observe formation of tyrosine Z radical in this case, which indicates the redox potential value of tyrosine Z is still higher than that of W1. So we further oxidize the system. Then finally in S4, we observed, the last manganese 1 is oxidized. And here we have still OW1 dot minus, and the nearest oxygen to OW dot minus is O4. So we analyze the potential energy profile for OW1 O4 coupling. And this is the potential energy profile, and the energy barrier for OO single bond formation is about 13 kcal per mole. And when we removed, and here we have WNW1, which arrived at W1 in S3. And in the absence of this water molecule, the energy barrier became much higher, so a few kcal per mole. So which indicates WNW1, this guy serves as a catalyst for OO single bond formation. And after proton transfer from D1 aspirate to 61, we have OW1O4 dot minus, and finally, as OO dot minus moves away from the manganese binding site, then it gives electron to manganese 4, and simultaneously W539, which had formed hydrogen bond with O4, is coming into the vacant O4 site. Simultaneously, the hydrogen bond pattern, which changed after proton transfer in the S0 to S1 transition, transformed from the post-proton transfer pattern to pre-proton transfer pattern, as you can see here. So now the orientation of the O4 order chain is completely changed. And as W539 moves closer to the manganese calcium cluster. And after O4, and after O2 moves completely away from the manganese calcium cluster, we got such O4 racking manganese calcium cluster. And actually, this structure resembles those already reported, for instance, Jimbaba's 3.5 angstrom structure and Chance's artificial complex, where they don't have O4 atoms, actually, which, and in my opinion, this implies the oxygen evolving complex is stable even if O4 is lacking. So this could be an indication that O4 can serve as a substrate of water molecule. Yeah. But I don't know about the O4 racking cluster and whether it is really stable. But if you assume that if you assume that O5 is a substrate water molecule, at any state, at some step, it must leave the O5 binding site. So you should have the situation where you have the O5 racking cluster. Okay, the last step, So we have, as I said in the previous slide, W539 was incorporated into the vacant O4 site. And in my calculation, we observed that it occurred in a concerted energetic, concerted exergonic process. So it's coming in and simultaneously forms mu oxo bridge over manganese 3 and manganese 4. But the distance between manganese and oxygen atom is still longer, about 2.4 4 angstrom, something like that. However, another water, so now we have the vacant W539 site. And when the new water is coming and occupy the W539 site, then we observed shortening the manganese oxygen distances to 2.2 angstrom. So which means incorporation of a new water molecule into the vacant W539 site is a kind of facilitates fixation of W5's new O4 molecule as a component of the manganese calcium cluster. Now, actually, this molecule, new W539, the next water molecule, which W538, which forms hydrogen bond with W539. This is the water which is absent in Shen's two-flush illuminated structure. So, in my opinion, the movement of this water molecule could be the reason why Shen's group didn't observe the presence of this water molecule in his two-flush illuminated structure. So this is how the manganese calcium cluster recovers in the initial state. Actually, it has still, the O4 site is still 2 protons. So this is just, this is before S0 state. I call it pre-S0 state where O4 is H2O. Then where these water molecules, for instance, the new W539 approaches originates. So we performed molecular dynamics simulation using the PS2 crystal structure, and we observed the majority of water molecules approach the manganese cluster using the water channel, which proceeds via glutamate 65 and glutamate 312. So I call this the glutamate channel. And quite interestingly, the 2 water molecule in the O4 water chain is not derived from the O4 water chain, but they are provided by the glutamate channel, because the O4 water chain is very narrow and all the water molecules are tightly fixed. So this is, yeah. So these two are coming via glutamate channel, yeah. So in this sense, I would say the glutamate channel serves as a substrate intake channel, at least according to my mechanism. So this is my final slide. As a summary, in S2, low-barrier hydrogen bond forms between W1 and D1 aspartate 61. And in the S2 to S3 transition, we observe oxidation of W1, formation of W1 dot minus. In S3, WN1 binds at OW1 dot minus due to the negative charge. And the presence of WN1 lowers the energy barrier for oxygen radical coupling between W1 and O4, serving as a catalyst. And as oxygen moves away, W539 is incorporated into the vacant O4 site, forming the mu-oxo bridge over manganese 3 and manganese 4 in a concerted hexagonic process. Yeah, and also W1 is incorporated into the vacant W1 site. So as a summary, substrate on the current turnover, substrate of water molecule on the current turnover are O4 and W1, and on the next turnover, W539 and WNW1. Thank you very much.
Yes, thanks very much, Hiroshi. Very nice talk. Questions? Morton.
Just one brief question. The water substrate channel that you show here presumably is filled with water. Now, does it conduct protons by a Grotthuss mechanism?
Actually, it's a good question. Yeah, this pink one is water intake channel, and there are some water molecules, but not completely filled. So they could move actually, but I think this can be. I also think that this serves as also a proton releasing channel. Yeah, I don't know, pathway. Yeah.
Could you clarify for me which it's your channel compared to Gary's 3 pathways? How did it map onto that?
I think he's talking about this channel, right?
And in your nomenclature, which one was it? You had 3.
Narrow channel.
Narrow channel is the O4 that
The green
yeah,
one, yeah.
yeah, green one, yeah.
That one, yeah.
And you said this
This
is
would be the
substrate.
broad channel.
Mm-hmm.
For proton release.
Yeah, in my case, this is also a proton releasing channel.
Yeah, that,
Right.
okay, so
Yeah.
that part's the same.
Yeah.
And on what basis do you rule out the other 2 channels being proton transferring channels?
I have actually 2 proton transfer channels. One is this green one, and the other one pink one. But so, yeah, depending on the S-state transition, yeah, the proton will be different. Proton uses different pathways.
Yeah. I really think to make assignments of these channels to specific functions, we need to do some experiments.
Sure.
And we need to, things like site-directed mutations to see if it affects water delivery or
Yeah.
affects proton release or things like that.
Olga?
Yeah, okay. I'm wondering about the changes of the hypothesis about the S3 state. It's of course you suggest that you oxidize a terminal coordinated water molecule. Is that right? Yeah.
Yeah.
And not the manganese.
Yeah.
And this is of course in stark contrast to spectroscopic data suggesting manganese oxidation.
Yeah, I know.
Actually, I think I'm pretty sure the spectroscopic data is correct. So I was wondering why you'd see this oxidation of a ligand in the simulations, whereas other people don't see it. What is the difference why, for example, Per Siegmann and others don't see an oxidation of a manganese ligand and you see it?
At least I include aspartate 61 in the other hydrogen bond network.
But I think others have done it before.
Okay, so question now, Peter.
So I have a question concerning, so you mentioned this radical forming on water 1
Yeah.
or
Yeah.
like that. So what's the energy difference for oxidizing the tyrosine? If you would like help it along.
No, actually, I didn't calculate the energy difference, but I have a good indication. I mean,
Yes.
tyrosine Z has histidine 190 as a hydrogen bond acceptor, and then we have aspartate 298.
Yeah.
And when we flipped the side chain of aspartate, then we observed formation of radical
Yes.
on tyrosine Z.
Yes.
This is because protonation state of histidine changes.
yeah. It's sometimes, at least for us, it's if you don't, you can easily end up in a minimum structure if you start from a
Yeah.
for example, by converging, helping first the proton and then re-optimizing the structure
Yeah,
might
yeah.
end up in. So it would be interesting to know the energetic difference.
Sure.
Okay, I've got one more question.
So, visualize, actually, I like your model very much because there's some suggestion, because we do some experiment on artificial model context. This is the false manganese with exchange ligands. So that is a key point for the oxygen involvement. Even we didn't get the photo oxygen involvement, but we do see the oxygen evolution from such sample. But I want to make sure you said the O4 can be formed to O bond, but in the structure, do you think it's protonated bridge oxygen or deprotonated?
In which state?
O4 in S1 state.
S1 state deprotonated. Yeah.
Deprotonated.
Yeah. No proton on O4 in S1.
But the crystal structure is strong hydrogen, as you point out, it's strong hydrogen. Actually, it can be mixed.
What?
in the structure, S1 state, okay?
Yes.
It is strong hydrogen bond between
Yes,
the
yes, yes,
O4
yes.
and the water
Yeah,
molecules.
yeah.
So that proton can be just come from O4. I would like to guess.
Yeah, I mean, at least donor and acceptor relationship changes in S0 and S1. In S0, O4 donates hydrogen bond to water molecule, but in S1, water molecule donates hydrogen bond to O4. Yeah.
Thank you.
Okay, we should thank Hiroshi again.
Thank you.
Thank you.